to be here today. I don't know whether you want now to give the floor to our speaker.
Yes, I think, thank you. I mean, I think that it's important and welcome to have the person who came from France to open the conférence là, and afterwards we give the floor to the two speakers of UCL. So I'll let you introduce.
Okay, so it's really my pleasure to welcome Betty today, Betty who very nicely accepted to join us. I have to say that today is the day off in France, so she chose to come, and probably it was good for us that it was a day off in France, so she did manage to come. So, too long, but I have a few introductory remarks about Betty. Betty is a spectroscopist, and she's now internationally recognized as an expert in exploiting satellite data for the study of atmospheric composition and climate changes. She is a senior scientist, directeur de recherche, directrice de recherche at CNRS. She's working in a lab at Sorbonne Université in Paris. She's also a professor. She's Belgian by nationality, and she's teaching at Université Libre de Bruxelles. She's also an affiliated scientist at NCAR in the United States. She published or co-authored more than 200 peer-reviewed round-table publications on spectroscopy, trace-based retrieval algorithm, validation experiments, data assimilation, analysis of pollution events, and of climate impacts. She was a lead author or a reviewer of the IPCC and of the WMO ozone reports. And in 2021, she received the Médaille d'Argent du CNRS, which is the top award, the top scientific award in France for scientific achievements. So today, she will give us a presentation entitled Temperature and Climate Gases, What Can We See from Space? The floor is yours, Betty.
Yes, thank you very much. Do you hear me well? Okay. Okay. Thank you for inviting me. I'll try to summarize in the next 20 minutes work that we have done, and most of the stuff you will see have been done by my students. Work that we have done during the last 4 or 5 years. But I've been working on a satellite mission, the same satellite mission, since I'm a postdoc. It means during the last 27 years, I've been working on the same satellite mission. So I'm just giving you a glimpse of what we can do, of course. So I had to make some choice. So this is the instrument I'm working on. So there's something wrong with it was working before, but can I have some help? Because it's not working. The animation was working when I did the test, and now it's not working anymore. Maybe it's the double.
So that's
okay. Yeah, it used to, okay, thank you. I'll do that. Okay. Yeah, it used to work with the arrows. But okay, this is the instrument I'm working on. It's called the YASI. It's a cube of 1 meter square, and it's sounding the atmosphere. So it's using the thermal infrared emission of the Earth, and the detector are recording a signal from which we can retrieve the signature of molecules. So basically, the instrument is making two things. It can measure temperature and it can measure concentration of trace gas. And there are currently 3 instruments flying. The first one was launched in 2006, and the last one was launched in 2018. So as I said, it uses the thermal infrared emission of the Earth, and it's a Fourier transform spectrometer that records what we call the spectra. And each observation is 4 diameters, and one observation looks like this. On this spectra, you have the spectral signature of all the molecules that absorb in this spectral range. And from that observation, we can retrieve trace gases. And I'll show you some examples. And in fact, we can retrieve concentration for trace gases for each of the absorbing molecules. So those are all infrared absorbers. So the main feature are climate gases. So the strong feature that you see here is water vapor, which is the first climate gas. And after that, you have CO2 here with two very big absorption features, methane, N2O, ozone. These are all the climate gases. And there are some of the molecules that absorb, like, for example, carbon monoxide. I'll show you, this is a very good tracer for industrial activity, for fires, because it's a tracer of incomplete combustion. And other species. There are some species that you don't see with this scale, but if you zoom on this signal, what we call here the baseline, it's where you have tiny, tiny signature, then you can see a bunch of molecules. The window that you see here is called the atmospheric window. It's where the infrared absorption escapes to space, in fact. And there are a lot of molecules that absorb that in that window. For example, CFCs are absorbing in that window. Okay, so I'm just giving you a glimpse of what we can do, because I could speak for until midnight, but I'm not going to speak until midnight. So let's first show you an example of what we have seen in 2020 regarding the impact of the COVID. So that's the same animation. Sorry, let's see this one. Okay, let's have a look of what we have seen in China during the lockdown in China. So we are here in February 2020. And as you know, most of the industry have stopped between Wuhan and Beijing. And we will use here carbon monoxide, the signature of carbon monoxide, to track the industrial activity and the fact that the transports, in fact, were stopped and so on. And what we observed here when we draw a map for this signal is blue corresponds to a 40% decrease in carbon monoxide. It's huge. Over China, we have never seen such a decrease, in fact. And so that's the type of map we get every day. Every day, there is an overpass on the morning and in the evening also. And so we could really follow, in fact, the drop of the pollution levels associated with the lockdowns in China. Then we did the same over other areas, but it's more difficult. For example, we did the same over Paris, but it's more difficult because there is less pollution. So we see a smaller signature. That's just to give you an example of what we can do. Let's see. Okay. In general, the Yas mission is on board of a satellite called METOP. There are 3 METOP flying, and in fact, the primary goal of this, the whole platform is improving meteorology, so weather forecasting. So that's the first goal. The second goal is to try to measure the concentration of trace gases. That's what my team is doing. And now we have added another capability, is because we have a record of 15 years of data that are coherent over time. We can also do some climate research. We can see the change in temperature. We can see the change in the infrared radioactive fluxes escaping to space. And we can see the change also on long-term climate gases. We can see the change on CO2, methane, and so on. So, but let's have a look on what's really great about this mission. It is that it has a very good horizontal coverage. And I'll show you what it can do for ammonia. Why ammonia? Because it's a small absorber, but it's a very important species, in fact, because it's released by agriculture, livestock, industry, and also fires. And I'll show you, it has the advantage of having a very short lifetime. So that there are things that you can do that you cannot do, for example, for CO2, because as you know, CO2 has a very long lifetime. So it's very well mixed. When you record the data, in fact, it's hard to see the sources. Whereas for ammonia, it's the contrary. It has a very short lifetime. It's a question of hours, maybe a day, sometimes over fires. And so you can really track the sources. So let's see what we get, for example. So originally, the mission, when we designed the mission, we never thought we could measure ammonia, in fact. But the instrument is so good, the signal to noise is so good that we can really measure even very small absorber. And ammonia, is, as it has a short lifetime, it's not present with a high concentration in the atmosphere. But in fact, we detected something weird. And when we draw maps, like this one, for example, we thought, what is it that is absorbing, in fact, over the Netherlands, over the Po Valley, at some area in Spain, for example? And after some research, when we look at spectroscopic database, we realized it was ammonia, in fact. And that's in fact the subject that gained us most of the attention, because there is no other satellite mission that was able to track ammonia so well. Since then, there is another mission in the US that can do it now, but let's see what it does. This is 1 day of observation over an area where there is a lot of agriculture. So each observation is this square with 4 pixels for round here. When we do 2 days, it looks like this. When we do 3 days, it looks like this. Let's average for a week, then a month, a year, and then you start to see really the patterns over the Nile Delta. And this is 10 years. It's really great because it's only measurement of ammonia. You see all the agriculture, livestock emission, in fact. And we can do that over the Earth everywhere. That's what we did, in fact. That's an average of 10 years over the whole globe. And when you look at specific areas, for example, let's zoom over 2 areas, you will see where the sources come from. So let's have a look here. I'll zoom in over this little red dot in the middle of the map here. We are on the frontier of Colorado and Kansas. Let's look at this red dot here. It's a source of ammonia. So I'm changing the transparency over Google Earth so that you can see what's under my red ammonia spots. Let's have a look closer, 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 like in a movie. Get closer again. You start to guess. In fact, it's thousands of cows. In fact, it's big. And so you can really see that, in fact. If you are not convinced enough, I'll show you another example. I'll show you an industry here that is releasing ammonia. Here we are over Uzbekistan. That's the Fergana Valley. It's very polluted. There is a hotspot of ammonia. Let's zoom again. And here, sorry, if we zoom again, Google Earth, that's a big industry that is producing fertilizer, in fact, and it's leaking. So you see the ammonia. And we did the same everywhere over the globe. There's a guy working full-time over 1 year doing that, in fact. And now we have all this data available and you can have a look. There was only one natural source of ammonia. It was due to, it was in Lake Natron, and we couldn't find any other explanation than the fact that flamingo are gathering there, and with their, how to say that in English, they poop, it's releasing also, it's a hotspot of ammonia also. So this is all available, but I wanted to illustrate here the power of average data over a long time. So with this 10 year, we really can track, in fact, the source of ammonia. And now more recently, we have started to do the same with temperature. Really try to dig and accumulate the data so we can really see the change in temperature. So let's see what we get. So this is surface temperature. This is just an average over a month in the summer. You know that, of course, when you move with latitude, the temperature are changing. And we can also zoom. So here, that's a Yazi observation again. What we will use is what we call the baseline. It's really the baseline here of the spectrum. And that's giving you directly the temperature, the ground temperature. It's like you put the thermometer in the ground, that's giving you that. It's really easy to do for an instrument. What is not easy is to get a very precise temperature. And for that, we need to average the data over long periods. And that's what we did, in fact. So to just give you an idea of how it's changing with the season, we get here a pattern. There's a small difference. This is the daytime averaging. On the right side, it's the nighttime averaging. And as you probably know, here some difference maps. As you probably know, the Earth is accumulating more energy, so more the temperature are higher over the Earth than over the ocean, for example. So we just showed here the results over the Earth. And there are some parts of the globe that exhibit very large change of temperature. Let's see how it does when we compare to models. This is, for example, sorry, that's in French, but I'll explain. This is coming from the last IPCC report, and that's the forecast for the the change in temperature when we will get 1.5 degree increase. That's what they talk about at COP26 now. This is how it looks like if we increase 2 degrees and 4 degrees here, depending on the scenario we use. As you see here, there's a large increase towards the pole. This is because the air mass are moving from the equator to the pole, and also there's something that we call the Arctic Amplification, and that's the fact that, for example, if the temperature warms, then the ice, in fact, is melting, and then the sun is less reflected by the surface. So it's like increasing this temperature again. So let's see what we get with the YASI data. So we can derive a map that looks very much like this, in fact. And as you can see, there's a blue spot in this area. And where is it coming from? It's because when you compare to models on the right side here, it's missing. And in fact, what they did not take into account in the model simulation is that the ice of Greenland, when it's melting, in fact, it's going to the ocean. And so like it's cooling this area. So yeah, let's see in detail what we get. I'll show you what we get with YASI. And for that, I'll use a very smart representation that was done by someone from UK, by the way. It's what we call warming stripes. Maybe you have all already seen that. It's a representation when you compare year to year or month to month with the same year or month average over time. There was a Tesla, in fact, painted by this warming stripe. There was some dresses or some shoes like this, for example. So let's see what we get with YASI. So these are the trends between 2008 and 2019, in fact, and I'll show you the warming stripes. So if you look at the trends here, it's only over 10 years. So we cannot derive much over 10 years, of course, but as the temperature has changed a lot over the last 10 years, we can really already see things even with only a 10-year record. So those are the warming stripes, in fact, when you average of the whole globe. And as you can see, you really see an increase in temperature for the last years, in fact. Let's have a look at closer at two areas. Let's have a look first at these green areas here, which is appearing like a strong increase in temperature. This is a natural phenomena. This is in fact peaking in 2016, and that's El Nino, this a very strong current that is appearing from time to time, in fact. So we definitely see that well with YASI. So part of this increase of temperature is associated with this El Nino event. Let's have a look here on the source of Greenland, as I just told you. Yep, here you see a decrease in temperature. And that's associated with the melting of the ice over Greenland. Okay, something else. Let's now zoom over two areas. I'll try here to illustrate the fact that the horizontal coverage is very good with YASI. We can zoom on we can zoom on Paris and see, in fact, the difference between the day and the night, and inside Paris and the suburbs. There is really a hot spot in town, in fact, associated with the higher temperature when people are working. And then when they go back to their home at night, in fact, you see that it's changing the patterns, and you really see the people going back home, and the temperature are increasing when they are back home. So we can also see that. So very small change of temperature. Here we are speaking about 2 degrees at the most. I'll show you something on the contrary when we have a city where it's colder during the day. Let's look at Riyadh here. In fact, it's colder during the day because it's surrounded by desert. And so the temperature of the sand is very hot during the day. And then the city appears to be like a cold island during the day. And at night it's on the right, it's the contrary. In fact, the temperature of the sand is going lower, and then the city appears to be hotter than the surroundings. Okay, my last stuff that I wanted to show you. This summer, it was quite hot at some area of the world. You all remember, in fact, the very large increase of temperature that were seen in Canada, for example. And let's have a look to what YASI has seen. In fact, it's here. So let's have a zoom over Canada, in particular over this city called Lytton, I don't know how you say it. There were temperatures there that were crazy high, like reaching 49 degrees, very hot temperature. And as you might remember from the news, after the cities was really burned by temperature, it got, in fact, numerous fires occurred, and it got all burned, in fact. We could see both of that with Yazzie, both the temperature that you see here with this map, in fact, the increase of temperature that is spectacular. And after that, we could also track the fires, and that's done, in fact, with the CO tracer, which is a very good tracer of fire. And that occurred not only over Lytton, but over other areas in the United States, for example. Remember that there were large fires over California, for example. And that's, you will see that in this small animation. So large fires over Canada, Siberia, they're all moving with the winds, and they're all mixing. So CO stays 2 months in the atmosphere. So you can see after a while, there's a big mix of CO, in fact. Okay, so I'll skip that one. Okay, so that's basically the end of my talk. And I maybe just an illustration about, because we are talking about climate. So you will know that, for example, the ozone hole is coming back every year, but we manage, in fact, to solve this issue by limiting the emission of CFC in the atmosphere. And it's exactly the same time of effort that are trying to set up with the climate regulation. They're trying to limit, in fact, the release of climate gases. And just to show you that for ozone is working well, we can also, in fact, follow ozone with the Yazzie mission. And these are, in fact, the temperature. So each year, the temperature are very low because we call it a polar vortex. They are very low over Antarctica in September. That's the end of the winter over that part of the globe. And then when this vortex develops, there are PSCs that are there, and there are special chemical reaction that, in fact, will place chemical reaction that will, in fact, be catalytic to destroy ozone. And that started this year, and that's the ozone hole as it developed this year. And we can compare it with those of the other years. This is all Yazzie measurements. And as you can see, it doesn't, it stays similar, it doesn't increase anymore. So what it means is that the regulation, the Montreal Protocol that was signed by all countries, in fact, worked well. And that's, the aim is that the Paris Agreement will be the same at one point, and we will be able, in fact, to limit the emission of climate gases. Okay, that's the end of my talk. This is in French, sorry, but okay. So I hope that with this talk, I could give you a glimpse of how great we have great satellite data now. That's not the only instrument providing, of course, concentration of trace gases, pollutants, climate gases, and temperature. But I just wanted to give you a glimpse of this great mission. Thank you.
Thank you very much, Professor Capot. I think for the clarity of the discussion, probably we'll take the questions of the two other talks coming from UCL.
Okay.
And you will come here and answer the questions.
Sounds good.
Later on. I think it's the best way to proceed. So we're going to move now for the UCL side. And the first speaker of UCL. The first speaker for UCL will be Dr. Michel Sanders, who is from the Earth Science Department. He's a climate modeler and a remote sensing specialist. He studied physics at the École Normale Supérieure of Lyon and holds a PhD in theoretical physics. He's now a member of the NERC Center for the Observation and Modeling, CPOM, and associate professor at UCL, as already said. He has 45 publications and a citation index of 20.
Too specific, sir.
I think I can continue, but really stop there because we have such quite extensive activity. But we have worked a lot, just a few minutes back, on ice coverage on the bows, and on the ice condition of the bows, and determining the accuracy of the ice cover of the bows. I believe also you are spreading your interest in other areas of ice observation. And so I'm sure you're going to let us know what you're working on today, and what will be your topic will be covered, which is essentially how can satellites help us to adapt to climate change. No, sorry, I'm wrong. The other speaker. How can satellites help to monitor?
Thank you.
So we'll adapt later on. To monitor.
Thank you so much, Serge. And very difficult to follow on this amazing talk from Cathy before. So yeah, I'm going to talk about another side. So maybe we had more of the atmosphere here with Cathy, and I'm going to talk a bit more on the water side, and maybe more on the polar regions as well. So and so this will be the kind of our first two talks about monitoring climate change from space, and Dan will take over on how to it can help us address challenges as well. So this is also the work of an entire team. So I'll give credit to my colleagues at CPOM, Center for Polar Observation and Modeling in Earth Sciences, and also funders from different organizations. So yeah, just a little recap. Let's not forget that maybe 70 years ago or so, we were for the first time looking at our planet from space, and that has been a radical change for our view of ourselves as a human species. So let's remember it's only recently that we have this view of ourselves that has potentially changed ourselves forever. Since then, we've had many satellites, and it's actually quite hard. I keep learning about new satellites. There's so many. Just keeping up with the existing data set, it is actually a challenge even for so-called experts like us. So I wasn't such a big expert on what was shown before, so I was very interested in that. Just to give a list, I'm going to go quick, but satellite remote sensing allows us to measure temperature, like we've just seen, from the surface of the ocean, the land. We can measure rain precipitation, changes of rainfall, changes of albedo, fires, sea surface topography, and sea level change. So I'm not going to cover all of this. I'm going to narrow it down, of course, but it's an amazing technique, and we have now petabytes of data, and we can really monitor climate change for nearly 40 years now from space, possibly a bit more. So there are techniques. We've seen one. There are techniques to measure the whole radiation budget, including Forum, that has just been selected a year ago to be the next ESA mission. And now we have a UK Space Agency as well that has a mission, Truth, to really improve the resolution and essentially the radiative balance at the top of the atmosphere, which is what controls climate and the average temperature of our planet, ultimately. So there are climate change missions more and more, and this is something the funding agencies are really pushing. Here I'm going to make the case for 3D. So we saw a lot of, they're kind of three-dimensional in the sense that there are layers in what we've seen before, but there are not many missions that measure the actual evolution of features in the third dimension. So altimetry is one of them, and I will try and convince you that this is important to have those type of missions as well. So put our 3D glasses on and try to understand this dimension. So just a little flashback, historical flashback. Chris Rapley, Duncan Wigan, Seymour Laxon, and many others were here at UCL, at MSSL, developing these polar missions more than 30 years ago. So we are continuing this legacy, and the UK and France have been at the forefront of polar remote sensing. So let's give them due credit. One of these amazing achievements was CRISAT-2 that was launched now 11 years ago, and we've had the 10-year anniversary earlier this year. And so this has been working for 10 years, and we've measured things like sea ice thickness for the first time, ocean topography, currents, waves, snow on sea ice, and that's an amazing success. These are the type of objects I'm going to talk about: altimeters, radar altimeters on the left, CRISAT, and now since 3 years ago now, ISAT-2, which is a laser design laser altimeter. Both are measuring the distance from the satellite to the surface so precisely that you can measure changes in the elevation of various quantities. So one of the things we've been looking at recently, actually, CRISAT-2 has changed its orbit to align at least over certain times with ISAT-2 orbit to measure at different frequencies with different resolutions the same surface, and that's some work we're doing to deduce the snow on sea ice based on this differential measurements of the elevation within centimetric precision from 700 kilometers altitude. So these have been real success stories of the last decades. So my talk is about, we talked about the atmosphere just before. Here is about the water. How can we measure changes of the water in the context of climate change? It's becoming particularly important. As is the case with the atmosphere, the whole layer of fluids on the surface of the Earth is very thin. If you put, it's the same as the skin of the apple compared to the apple. So if you put all this water into a sphere, it looks like this. And that's all of the liquid fresh water. These are the lakes, and you can, so sorry, these are the oceans, this is fresh water, and these are lakes. I believe I'm right. I'm confused. So the point is that this is, it looks suddenly very small. So it's a very fragile system that we need to monitor very carefully to understand, you know, our kind of survival essentially. So is the atmosphere. So if you break that down into components, most of the water is into 97% into the oceans. And so you have glaciers, groundwater, and then you have fresh water into lakes and rivers and swamps. And then you have surface waters and even smaller components shown here. So I'm going to go through them one at a time and show you how we can measure the change over time. So if we start with the oceans, there are techniques called altimeters, as I said, the traditional techniques pioneered 30 years ago to allow us to monitor the distance from the satellite to the surface and monitor the change of this elevation over time and over seasons, and deduce things like currents, but also sea level rise. So the technique is based on the shape of the return of the echo that you transmit will inform you on the roughness, the waves, the elevation, and even things like oil spills and things like that can be captured with this technique. So this is showing you now CRISAT-2. This was an innovative technological development linking with work done at MSSL and so on the engineering side, how to narrow down the beam. And this changes the shape of this echo and makes it much more precise in a sense. So it's called high resolution SAR, synthetic aperture radar. So they have both been huge success in monitoring changes in the ocean. And this is the kind of data we have compiled now for the last 30 years of almost 30 years to monitor sea level change. So we can have now a good idea of the total contribution to sea level change and decompose it into contribution from thermal expansion, glaciers, Greenland, Antarctica. And the sum of these contributions are in red and the observed in black. And so we have a really good understanding of these trends over the last 30 years. These actually accelerating trends. So this is one of the big challenges discussed at COP is of course, this is a high risk scenario for our populations. Sea level rise, like temperature, is not homogeneous. So there are regions that have much more enhanced sea level rise than others. Some are actually declining for various reasons. But importantly, a lot of the populations are coastal. So they are very likely to be affected by this sea level rise. And Dan will talk about this in his talk. Coastal erosion is one of the challenges that even the UK is facing, and many countries at lower latitudes are really exposed to. We heard a lot about this in the last week in COP26. If we go to ice caps and glaciers, that's my specialty, our group specialty. We've developed this tool, CRISAT, as I said. And so CRISAT has been an amazing, monitoring, cryospheric monitoring satellite mission. It was one of the ESA Earth Explorer missions. So it had a science goal. And we see here what it did for Antarctica. It has a triptych of measurement: land ice, sea ice, and oceans. It turned out that it became much more than that, and it's been used more and more for rivers, for all kinds of measurements even over land. We will see in a second new techniques that have allowed us to measure changes over the glacier, ice caps, over mountains as well. It has also allowed us to refine the bathymetry of the ocean, by the way. So there are kind of, unplanned discoveries that we had thanks to CRISAT. So if we move to the northern hemisphere, we can see Greenland. Again, changes the rapid melt of Greenland. And also we can see when it appears here, the changes that we will see over sea ice. So if I accelerate a bit, you see that the cumulative volume loss has been now quantified thanks to cryosat over the last 10 years to a higher resolution than ever. And similarly, over sea ice, we've been able to measure changes of the sea ice thickness over the last 10 years. Actually, here it's showing the ice volume every winter as the ice is freezing. Just a week ago, our team published the first measurement of sea ice thickness in the summer. So this was not possible until now, and we will fill the other half of the year here and see how the ice is melting in the summer thanks to this technique as well. So if you look at longer time series, you can see that more than half of the total volume of ice has disappeared over just 50 years at the end of summer. So in a sense, we've already lost almost all the ice in the Arctic. So it is possibly the most emblematic signature of climate change. And it's a very fragile system, so it's very sensitive to warming, of course. So sea ice matters because it's, as we've seen in the previous talk, via its positive albedo feedback. It's very white. When you melt it, you put more heat into the system, and this kind of positive feedback, kind of catastrophic feedback for our system. So it contributes to more warming than you would predict without accounting for this positive feedback. So this is, if you have warmer temperature, you have less ice, more absorption of energy, warmer ocean, and that leads to more melt. So it's a kind of positive feedback loop. So also, I find it's a very nice telling thermometer to really make you understand how our CO2 emission impacts sea ice. In fact, there is almost a rule for every ton of CO2 that we emit, we melt 3 meters square of sea ice at the end of the summer. They are physical, it's not just a correlation, there is a causality here that explains that with physical models. So when you go to your favorite American Geophysical Union, you are contributing to 10 meters square of sea ice melt. When you buy your iMac, you contribute to 3 meters square of sea ice melt. So I think it's quite a telling analogy and ruler to understand my impact, our impact on climate. Glaciers and Greenland ice sheet are shown here. Again, a combination of altimetry with gravimetry allows us to get a good picture of how much ice we're losing from the land ice, different from sea ice. And you can decompose in terms of Antarctica and in terms of different regions of Antarctica, the east, the west, and the peninsula. And we know that the West Antarctic ice shelf is the region that is likely to completely collapse in the next year. So there is elements of irreversibility here that we are talking about and included at COP26. If we are reaching a tipping point for West Antarctic ice shelf, several meters of sea level rise irreversibly, for tens of thousands of years, irreversibly built into our system. So if we keep pushing our system to 2-3 degrees consistently, this is going to go irreversibly. And so there are ideas of tipping points here that you must be aware, and that are still being researched. So we're not completely clear about the unknown unknowns as well. Unknown unknowns. Something like that. So glaciers in decline are also monitored with cryosat. I'm going to go a bit faster, thanks to a technique of cryosat called swath processing, where you can actually really go at 500-meter horizontal resolution and make this kind of timelines over 11 years here of each individual glaciers losing ice mass over the last 10 years. So this was a technique pioneered in Edinburgh by Noël Gourmelin and others, and it's really striking how our glaciers are also disappearing rapidly. And so it is a sad state of affairs. If you put all this ice together since '94, it's in a sense not so impressive, I find, because it's the beauty of a cube or a sphere. It looks much smaller than when you spread it over a larger area. But that cube is what we melted. This is New York, and so it's a cube of typically several kilometers wide of ice melted over this period. And this goes into the ocean and raises the sea level. You can do the math, try and do, I do that with my students, try to see how much a cube like that will raise sea level. Groundwater can be monitored from space as well. This is very important for resources and populations. thanks to techniques like we had Marek Zibert earlier, gravimetry gives you a differential gravity field that allows you to see very precisely change of the gravity and the mass of water inside the land, hidden in other ways. So if you see at relative acceleration of the two Grace components here, you can detect so precisely the gravity field that you can make maps like this of gravity anomaly. And you can see those seasonally, and this indicates you where is the water, has it changed, the groundwater resources have a mass and is visible from space, detectable or deducible from space. So here we see mass anomalies in August 2020 compared to a baseline of 2005 to 2010. Water on Earth on lakes, you can monitor that from altimeters as well. So here I'm showing from images, but you can also measure this with altimeters. So again, some regions are really, the effect of temperature increase is really dramatic on some regional lakes. And rivers is the thing we hadn't predicted we were going to be able to see with CRISAT, but actually different altimeters put together, in particular CRISAT, can allow you to track changes of sea level seasonally, but also over decades. So we've had now great success with that. So I'm going to, I hope I gave you a good overview of how important this third dimension is in monitoring changes of elevation, and that we need to continue with these 3D glasses and really push for a follow-on mission. There's a mission concept that's still being, it's hopefully likely to be funded, and it's a Copernicus mission called Crystal to continue really the legacy of CRISAT 2. And so this gives you an overview of the missions that have been that are flying already, and also the timeline. So here we're about 2020. We are kind of living in the golden era of polar altimetry. We have Sentinel-3, ISAT-2, CRISAT-2, Altica, Chinese Indian cooperation, and we're going forward. And we must make sure we don't have a data gap in the years to come. So Crystal will allow us to continue to monitor all the way to 88° north. So cover all the sea ice, all of Antarctica, and monitor land ice changes. Just to say that this links, of course, water is essential for our survival. We are, 80% part of water, but it's what we rely on. And so a lot of the sustainable development goals that are being discussed, Dan will talk about that, and also at COP are intimately linked with water. So I think I'm going to stop here, hopefully roughly within time, and give a bit of time to Dan to see how we can tackle issues with monitoring from space. So yeah, thank you very much. And we'll take questions at the end, right?
Yes, indeed. So, we continue the conversation now with a talk given by Professor Dan Osborne, and it's the other side of the coin. How can satellites help to adapt to climate change? Just a few words about Dan. Dan Osborne is a professor of human ecology at UCL Earth Science Department, co-chair of the UCL Environment Domain, and editor-in-chief of UCL Open Environment and Open Access Journal, with an open peer review process. He's interested in the links between natural resources and well-being. He was co-lead of the People and the Built Environment chapter of the second UK Climate Change Risk Assessment Evidence Report. So I think, Dan, you are perfectly, I would say, tuned to indicate to us how satellites can help to adapt climate. The floor is yours once the technology will be yours.
Well, thank you for the intro. I want to take quite a different tack now. I want to think of things from the perspective of a local community that's got to adapt. Okay, and then, what can satellites already do and what might they do? So, where might we need to go to help communities adapt? I think there probably is a key role here, but it means carrying on this line that the last two speakers have described, particularly in things to do with heat and water. Those are the two things that cause problems from climate change. And the first speaker talked about the success of the Montreal Protocol. Why did Montreal work? And what is more difficult about making the Paris Agreement work? So Montreal worked because there was a human health endpoint. So too much of an ozone hole increases the chances of cancer, skin cancers. You can cost that. You know how much that would cost in terms of dead people and cost to health services around the world. So policy people could sit up and say, oh, we can't have that. And also with Montreal, there was a very easily identifiable single cause and some easy, relatively speaking, technical fixes, and an industry that was quite innovative anyway and competitive. So they were open to the question of change. So give them time, they could replace the causative agent. So governments around the world could sign up to Montreal, and we knew how to monitor it, you know, these matters. So we had a way of checking on progress as well. So we had one cause, one main effect, a technological innovation not too far in the future, and ways of monitoring it. So that was easy. Climate change is not like that. Climate change has a gas that is to drive it, which is widely distributed in the atmosphere. It has multiple kinds of effects. For example, on ice, as Michelle showed, it has multiple endpoints. It has lots of different sectors, including you and me sitting in this room now, which are sources of the gases that drive climate change. So it's a really difficult problem to tackle. Lots of challenges are embedded in that. So if we have a look at this, how to make it move on? Click. Oh, sorry, fine, got it. I didn't hit the button hard enough. Yeah. Okay. So what's happened at COP? What's happened recently? What's happened when the UK's third climate risk assessment was launched a few months ago? The community came off the fence. Gone, in a sense, was the language about being uncertain. If you say you're uncertain to a member of the public or a politician, they might think you don't know what you're talking about. So the messaging has changed. It doesn't mean uncertainty in observations or in model outputs has gone away, but the community's messaging to the public and to policy people on issues like adaptation has changed. And there's now little difference between the messaging you see in the media and what was said at COP in the opening session. If you listen to the opening session at COP, they mentioned all these things. Wildfires, right? Droughts, flooding, sea level rise, and storminess, and things of that kind. And the key thing about all this is we only have one planet. So the way we run our economy at the moment, it is run on the idea that when we come across an environmental problem or something like that, or we run out of resources, there will always be a substitute available. There will always be a technical fix because we are so innovative. We can find new resources, but there is no substitute for this planet. We don't have another planet next door that we can all move to. If we run out of resources here, that's it. If we make the planet unlivable, because temperatures over 50 degrees are in some parts of the planet already, then we're in real trouble. So this kind of very clear messaging is really important. And what that has done as well is lifted adaptation up the agenda. Because some parts of the world are already at 1.5, And that's the target that Paris has got. So we're already behind the curve. You know, some parts of the world are already getting to 1.5. We are behind the curve because serious impacts of climate change already begun. So in the preparation for the COP, as well as talking about heat and things of that kind, the World Meteorological Office organization rather issued its latest, an early view, if you like, of the state of the climate. It does these reports quite frequently, roughly annually, but usually the reports are not released until they've had a very good look at all the underlying data and everything else. They're very, very careful, very high quality kind of report. But they brought this full report forward. And one of the things that really struck me, because I'm quite interested in coastal change, was that we've now got a sea level rise rate of about 4 millimeters a year. 100 years ago, it was 1 or less. So we're now at 4. And as Michelle just said, it looks like it's accelerating. And if it starts to accelerate, then we are easily going to get to 1 meter of sea level rise by 2100. That's really quite serious. If the West Antarctic ice sheet melts, well, let's move London. You know, we can't cope with 5 meters of sea level rise. So, you know, we need to move quickly on those emissions, but adapt now because and plan to adapt, because that is going to become absolutely essential. You've got other things to deal with in the water cycle in the oceans. They're constantly acidifying because the carbon dioxide is in there, and it's more acid than at any time in the past 50 million years or more. These are remarkable pieces of data that have emerged from the science, and satellites have played a very significant role in this. And the variability in rainfall, which is a real killer for some communities, is causing floods on one hand and severe droughts on the other. So you have, you know, a hydrological cycle here, which is so variable now that you're getting extremes that people would not have imagined previously. And the same is true for heat, as we saw from the data on Canada and places like that. I would never have believed that Canada could get to very nearly 50 degrees. But then it was only 2 years ago that we had a high temperature in Iran of something like 54 degrees. These are unlivable temperatures for people. You know, and now we've had that kind of temperature repeated in California. And California is in a classic long-term drought situation. A lot of America, the reason for sitting up in America is it has drought on the west and probably the highest levels of sea level rise on the east coast. So these are the things that are making huge differences to people. But what's the challenge of adaptation? Well, first of all adaptations are local. You can't say there's a global way of adapting. These all have to come down to local people. And we have to take the data we've got and see that translated into action. And that can involve all sorts of different levels of activity within a community. So I asked a group of 200 people from a Sussex community recently to give me some idea of what was on their priority list for dealing with climate change. All these people had come to the meeting to talk about climate change. And when they listed these things, I was quite surprised. Education was one of them. They wanted their children to have more education about what to do. They wanted choices. How could they have options to act, a bit like a policymaker, really? But they wanted practical options to do. Were there things they could do to reduce the levels of pollution from various sources? Could they change the way they managed the land in the local area, farmers amongst them, and things of this kind? So quite a surprising list of things. But one of the things that really surprised me was they were concerned about food supply. Where would food come from in the future if the temperatures were so high that people couldn't grow crops because of drought? So the public now is beginning to get to want to tackle some of the issues that we've been dealing with over time. So some of the things that satellites already do could really address this issue, but communities don't know how to get hold of the data that people in this room generate. So it's a question of trying to convey some of that information and trying to address perhaps the issues that really matter to them. So data is needed probably on all these things on the left-hand side of this slide. heat, water, land, soil, oceans, ice, woodlands and forests, green and blue spaces, and crop yield. So I talk about two of those. Coastal change perhaps are the issues to be addressed, and urban design in one way or another. What are the risks, actions to be taken, benefits delivered? I've tried to summarize those a little bit there. I mean, if we get sea level rise wrong, a lot of people, or how to manage it through an adaptive management approach, which means perhaps investing now for worst case situations in the future, because it's cheaper if you invest early. But if you don't do that, then we'll have to deal with large scale migrations. How are we going to move London and Shanghai and all the other coastal cities in the world, New York, things of this kind? You know, the bills for protecting them temporarily are already approaching 100 billion. And that's a lot of resources to have to put to one side. In urban design, if we get that wrong through overheating in our old building stock, UCL's building is pretty old. Overheating, we're building now properties which are not climate ready. How are we going to adapt those when we've already built them? They're going to be standing for 100, 150 years. So we have a lot of challenges, and it's going to be very expensive to do. But from the COP, we were talking a lot about people and nature. So we've already seen these, the fire thing. Why do we keep, all of us have referred to the fire images that the satellite systems can produce? Why do we do this as people? Why do we pick fire? We pick fire because humanity deals better with extreme events than it does with long-term trends. That seems to be a behavioral characteristic of people. You can find Greek philosophers who discuss this issue. They talk about accidents ruling us rather than anything else. So we're okay with extreme events. We can tackle those. It's here today and gone tomorrow, maybe, a bit of luck. And we need to stay out of their way. So that's one of the things we do. Where we're less good is picking up these trends. And so satellites give us a very important thing, which I think is important to the culture of people. That is, how is their place changing, the place on which they live? We all have special neurons in our head, which give us a sense of place. Nobel Prizes have been won for that kind of thing. And so this issue about whether we feel at home somewhere and how that is changing, it's really important. That is one way in which we can capture people's attention to get them to move on into these areas of adaptation. And this is something that can be done routinely. This issue of phenology, this is the biology speaking. Biological signals of climate change have been around for 150 years. And we need to pay attention to what the biology is doing. So although this is a climate crisis, a lot of it is to do with the biology. Let me give you a few challenges, perhaps, of what could satellites do in the future. We've seen very clearly from the last two talks what satellites are already doing. Let me give you a challenge about the coast. So if sea levels are rising, coasts are changing. Coastal communities are at threat. So if you look at the top image here is the coastline in part of Sussex in southern England in 1870. This was mapped by the Ordnance Survey. This is the map. It's the contemporary Ordnance Survey map for the same coastline. It doesn't really superficially look as if much has changed. This is the Google Earth image. And I've picked some of these images simply because these are the kinds that communities in this area talk to me about. They talk to me about the changes that they are seeing. So these are the kinds of images we're looking at. And this is the coastline at the bottom from just a Google Earth image. If you actually do some measurements on here to have a look at how much of this land is still good quality agricultural land, not a resource we can do without, because if we reach 10 billion people by 2050, that leaves us 0.5 hectare of good quality agricultural land on which to produce our food per head. So land availability and how much of that is a challenge, not only near the coast, but elsewhere, that perhaps the satellite systems could help us a lot with. That's much more about the nature of that land. If you do these measurements, then you find between 1870 and this Google Earth image, which is about 2020, that about 90 meters of coast seems to have disappeared. So that's quite a lot of land to have lost in a particular area. If you really then focus down and look at the kind of coastal change that you can see in an area, And Michelle cautions me about taking images, which are at different times of the year, maybe. So no excuse for that. I've snapped these straight out of the Google Earth thing, because this is the kind of data and imagery that communities get access to and can use. If you look here in between 2001 and 2020, then you can see in this area, which was agricultural land, this has gone completely. It's been replaced by shingle. That shingle has come from the beach, which has degraded. You can see here, this is an old seawall, not a good quality seawall. It's a poor one, only about 1 meter wide maybe, and made of old style concrete, but that has broken through completely. And the only way the people who run the business is the back of this car park, a small cafe, it's an amenity use. A lot of people use this area for walking. And now about 1/3 of the car park is occupied by gravel, which is in shingle, which is the only way of stopping the sea sweeping inland for a considerable distance. And the sea has broken through further along the coast quite frequently. And again, the coastline has been set back by the Environment Agency 10 meters, just as a result of 2 coastal storms. So there are rapid changes going on the coast, which makes differences to people. And just in these 2 images, there's a loss of farmland, a threatened business, just one at least, a loss of amenity land and cultural heritage, etc., and coastal defences swept away. So more problems storing up for the future. This is what it looks like in practice. And the area of coast here, you can see that has disappeared. This was the old seawall line along here. This tree is one of the things I use as my marker, and I can tell where I am because there's this gorse, which is here. And I did not think when I went down to start to look at this beach in 2011, that the beach where I used to walk would have washed away entirely by 2020. So a lot of the markers, the fixed points I was using to measure the rate of erosion of the coast here have gone completely. So is it possible to monitor this kind of change with a fantastic satellite technology that we've got? Because communities all around the world will need this kind of information. They'll need to see what's happening now and how it's changing and how they can plan for the future. Because there are already communities that will have to move by the middle of the century. But the arguments about whether or not a community will be viable or not are absolutely intense. And hundreds of millions of pounds are at risk, and people's livelihoods, their health and well-being is all threatened in these kinds of areas. So what should we be doing to help this kind of global problem that has its different manifestations locally? Well, we need those first 2 bullet points. And if we could get those first two bullet points measured accurately and very frequently, so we can really measure the rate of change, particularly in the most vulnerable areas, then we could do the bottom 3 things. That's what are the real economic value of all those assets? What better risk assessment and risk management procedures could we develop? A base, say, around adaptive management. So you invest early rather than late, and you get a realistic view of what's going to happen in the future. So London's Thames Estuary 2100 plan gives you a clear indication about how much sea level rise London can cope with and what steps are necessary to make that possible. But to do that, we had a lot of data. On the coast itself, the situation I think is less clear. And you need to do this bottom one. If you have the science data, the local communities can take it on. They're perfectly capable of understanding all the limitations and things like that. So they can do things. More of a challenge than that, perhaps, is what do we do about designing urban areas in a better way so that they become climate ready? More than half the world's population live in urban areas, so this is important. They mustn't overheat. How can we do that? One way of doing that is to make better use of green and blue space in urban design. when you're developing new settlements and things of this kind. And I'll show you an image at the end that I think shows that rather graphically. The trouble is for communities in trying to think, how can they change their community to adapt to climate change in some way, to provide more shading, to reduce the heat island effects and things of this kind. When you look at what people have got available to them in terms of data, then they go to things like maybe OpenStreetMap if you're lucky, but they usually use Bing Maps or Google Maps or something like that, or they might look at Google Earth. And these slides show you the different way in which green space in urban areas is mapped at the moment. There's no consistency here about how this is done. And one of these images is from the Ordnance Survey as well. So it's very difficult to establish a dialogue with the community when all the different individual members of the community have different ideas about the structure of their town or their city. And these very local things are terribly important to people, because sometimes people don't know what is available to them 5 streets away. Yeah, people are so tribal that they really focus on their own area, and what's just around the corner they might not know. One of the other profs at UCL tells me that there are some communities 2 streets away from the Thames, deprived communities, that don't realise the Thames is there. Okay, so this local scale knowledge is going to be really important if we're going to get whole communities to adapt. And we need to do these measuring of assets in urban areas so that the planners can get a better idea of how to measure change. Many of these industrial units in this particular town are actually built in a flood zone. So it's quite important. But if we want to tackle things like heating in urban areas, then these kinds of pieces of information coming in from satellites are really very, very powerful images. And I think the power of some of the simple images that can be produced is illustrated quite nicely by this image of the heat island effect in London. What it shows quite clearly is if you want a cooler London with less urban heat island, less morbidity, fewer deaths, more efficient workplaces, then you need to have more green. And London is one of the world's greenest cities. But look at the temperature differences between the parks in London. This is Hampstead Heath, I think, and some of the more urbanized areas. Some of the modern developments that take place in London have far too much concrete, vast areas of concrete that could have been green and could have provided shading and shelter to the buildings. So it needs a radical new way of looking at how we design urban areas. And I think this kind of material that comes in from satellites is a really good tool to use with urban planners. But we don't have an urban planner satellite way of talking to one another. So we need those kinds of networks and the kind of technology that will produce high resolution images of urban areas. And I think there are other things in this area that we can pick up. Developers like to build on greenfield sites because it's easy. This image shows you a small town in Sussex in 2001 and what the extent of the land take will be by 2040. That's due to us moving into these areas, moving out of urban areas, driven by COVID, for example, and things like that. But we don't know what we're losing here. We know what we might gain in terms of housing, but we don't know what we're losing. So can we get more information from satellites about these rates of change? We can do this kind of thing from aircraft, but satellite imagery with CubeSats and things like that, they may be a more efficient way of measuring the rate of change. And the rate of change can be quite rapid. Almost this whole area has now been built on. And that has happened in much less than a 10-year period, perhaps over 5 years. This has all now completely disappeared, but nobody talks about the resources, etc., that have been lost there. The ability to store carbon, for example, if the land is used in particular ways. Other things that are happening are there are large-scale changes in land use going on all over the world. Here, for example, if we take a reference point around here, that field and this field are the same. This is part of an estate in Sussex, which is rewilding. And in these images, a lot of this stuff will be, aerial things, not satellite imagery. You can see the amount of growth of trees and things like that have happened over a 20-year period. So there's an entire change of land use over time. Well, what is that worth? If we can actually accurately estimate those kinds of changes from satellite imagery, we can calculate how much extra carbon has been stored. And this is a way of balancing the carbon budget and helping land owners, farmers, etc., adapt to changing climate and do this in a way that will bring them economic return. But we do need to have those kinds of tools available. And I'm pleased to say that the financiers are all beginning to get interested in it. Really, at the very fine detail, we all need to be aware of things like other risks of climate change, which come with increased amounts of surface water flooding. Many major cities will be knocked out of action if they encounter a 40-millimeter rainfall event or a 60-millimeter rainfall event over a number of hours. There was major flooding in London and disruption recently. So in countries like the UK and other developed countries, it's possible to use all sorts of different types of data to work out more about surface water flooding. But in some ways, surface water flooding is a hidden risk of climate change we need to adapt to. And if we could try and get better terrain models for urban areas, we would be able to prevent the damage from surface water flooding by encouraging people to take up very simple pieces of tech that would stop their properties and their businesses from flooding. Because people suffer repeatedly from this idea of surface water flooding, and it can almost occur anywhere, but particular places are very susceptible to it. And this is Bloomsbury in London, not far from UCL, and there are even parts of the campus which are particularly susceptible to surface water flooding. And they are areas which you would not want to flood because of the gases and things like that that are stored there. So there are good reasons for doing this kind of thing. And I think that satellites could help us by giving us a lot more information on the nature of an urban area. And I think there, I'll stop. These are the other things that we could discuss a little bit. And they're all things we will have to take account if we want to adapt successfully to climate change. And some of those things have been addressed by the other speakers who showed us about the satellite things that are being dealt with already. Thank you.
Thank you very much, Dan. It's really sometimes anxious to hear what you talk about. Based on anxiety. So I would like to ask to the two speakers maybe to move to this table, and we'll start a small session on Q&A. I believe you have some questions, so just stand up and start the question. Yes.
I was wondering if the current infrastructure of satellites we have don't give us enough data, and the problem isn't that we are not analyzing data to drive the information on, because for example, if I'm going to design a new satellite, let's say, so what extra information do we require to do that, which is not already there? Because you showed me that very nicely, showed some pictures side by side, the changes, things like that. So I'm wondering, from have we done enough data analysis based on those pictures, and we basically exhausted all the information within those data? And the problem is, do we need more data to make more information, or so that's what I'm interested in.
across. I think, as Michelle's talk showed, so there was a satellite where the people were thinking about ice, but actually there's loads of other stuff that it's able to do. So there is probably a lot of data out there which will be very useful for communities to be aware of. But the issue is, how do we just get that and move it down to, or put it in a form which people can understand? So I don't know whether I'll put the quote up that the senior policy, the technical policy advisor said to me when I said, oh, I'll do a model of this and I'll produce a tool for you. And it works like A, B, C, D. And he stopped me and he said, if I have to push a button beyond A, maybe I'm not really interested. So we've got to have a way of getting the data processed in a way that produces the output kind of variable that really interests people. And we're not doing those, we're not having those discussions, I don't think. Well, not enough. We must be having them somewhere, but we're not doing it enough.
One quick word. So just to say, you're right, these petabytes of data being produced now every year. So, and very few of these petabytes go to the policy side. So this is the junction between us and the policy to make. There's a lot of work to engage, create jobs in the market and so on, which is happening to many decades, and it's still exploding. There's a market in London for insurance. There's all kinds of things that are exploding now. But it took a little bit too long.
Yeah, I think we get better organized now between the scientists and the ones that take decisions, because we have this long-term program, like the Copernicus program in Europe, which is very efficient in monitoring different aspects like land, ocean, atmosphere, and that helps, I think, because we are all making an effort to make the data available and that it's useful to a wider community, not only for scientists, but to a wider community.
Yeah, just to say that is right. The program Copernicus is designed with that in mind. Right? It's an operational program, and it's meant to address concrete, operational challenges. And it's multi-billion EU, sadly. So we have to find a replacement if we don't want to pay to the Copernicus. Yeah.
Just do you see major machine learning can play for data?
Yeah, for the temperature maps that I just showed, it's neural network deriving because we have so much data. It's like for the less instrument, this is really great. For the less instrument, there's one data every 3 seconds, and so that's the instrument. So it's like we are overwhelmed with data. So we use neural network to derive everything.
Other question? Yeah.
We follow up on this question about data and machine learning. How long does it actually take from collecting the data, calling the different functions, to actually producing and just publishing the decision makers? Because is this like weather forecast that is quick, or like in particle physics and so on, it takes years sometimes to exactly.
Okay, I'm lucky enough so that the instrument I'm working on is a meteorological instrument. So I get the data less than 2 hours after the satellites, and we process everything automatically. So usually can derive a map within 3 hours. So it's really fast. And we have designed everything so that it's fast.
Yes, so I think it's a little bit slower usually, but it's also there's a near real-time product within a day that is not yet assimilated. Part of that are functional, but from the pilot it is not yet operationally assimilated into the net office. But it's something today, just a few hours. But Copernicus has the operational dimension, so they probably will aim for hours as opposed to days. And but But there are other things that we discover about climate timescale, right? So revisiting 40 years of data is something that is also very important to us. And it has to say.
I think some of the most convincing pictures we've got that come from satellite material. So, I mentioned Duncan Wingham. Duncan's been chief executive of NERC, and when he was giving one of his early talks, he used 5 images, which are almost all come from satellite information. And it's that ability to get a clear idea of trajectories, like the loss of sea ice or the rising sea level, and to make points. That one of Duncan's points at the time was, oh, we've just changed the scale in which we measure sea level rise from a millimetre scale to a centimetre scale. It's that kind of impact, I think, that you can get from those lines. And policy people really like line graphs, simple things. Why do they like that? Because when they're doing their risk assessments, they need to know when things become entirely intolerable, mustn't go there, so what's the worst case? And then what's the place where the smallest amount of change occurs, where action is required in the next 5 or 2 years? It's those kinds of questions, and a line graph helps with that. So if you can actually really boil the data down quickly to build that line graph, that really is very easy for people to take on board. Line graphs and images.
Yeah, another question? Yeah, go ahead.
Yeah. So all 3 of you talked about how like the value of having satellite data, and then you talked about how this is important because in the sense local communities can see how climate change will affect their community, and then they can proactively react to it. And my question is, how do you make this information accessible to everybody? How do you make sure people are actually interested in looking at this information? It's like, younger generations were taught, kind of climate change in their classes, but this doesn't happen everywhere. And then, the generations maybe aren't aware or just don't care in that sense. How would you do that as it's not through education?
Yeah, that's I think that we can learn more on it. But just to say that I have a good example of something that can work. So there was a UK Canada EU program that was funded, and I big on this only yesterday. So in that program, we're trying to take high resolution satellite imagery with the Inuit partners that are leading the proposal. So it has to be indigenous, locality led, because it has to address a real need. And so they are the need that they identified that is travel safety. And so the satellite comes just to support that need and address that specific need. And the whole proposal was empowering the localities to address that specific need. But there are millions of examples of it, so I'll let that come on.
So something that I was quite intrigued by a few years ago was that the American Corps of Engineers, for those of you who don't know, they do the coastal flood defences in the States. So they have a fund now, I think it's still running, for local communities who are at risk from sea level rise or from storms, to engage with the Corps of Engineers and work out what would be an adaptation that suits that particular community. And some of that might involve hard engineering, or it might involve taking steps locally to protect sand dunes or something of this kind, stabilise in some way. So, if the American Corps of Engineers can take that kind of approach of putting the community first, then it's like Michelle's example as well. And there are lots of those examples, and the trouble is, we don't want people to go around waste time reinventing the wheel. We want to take those good examples and tell other people about them. But at the moment, there's not a clearinghouse for doing that. So I'm talking to a group of people where it might help make that possible, but long way to go as yet.
Yeah, for example, in my group, I have like 24 person in the team, and the last person I hired was a graphic designer, because because I thought, okay, we are scientists, but we are not trained to get our results to a wider community. So all the communities that you have seen in my presentation, it's thanks to the fact that we have higher graphic design. I think it's a new way to think about stuff. They are also trying to use what is media, like I don't know if you know that's deconversation. It's a media that is really it's like a newspaper, but it's written by scientists and there are editors that are changing what you write to make it understandable by a wider public. And for that, for example, when we have a very interesting article like the nature or something like that, we try to explain it in a very easy way and to publish it through the conversation, for example.
Other questions? Yes, Nina?
Maybe it's a less scientific question, but it's more about your analysis of what is going on at the moment at the COP26. What would be your expectations or your fears? You have been part of the reviewers of the IPCC committee, and most of you probably follow quite closely the information or the scientific data which have been produced. So what is your, not only personal but also scientific feelings about what's happening?
So it's quite technical even for us scientists. I would say that all the last thing of the last few days has shown develop. What I know better is what I decided at the start is like trying to make an effort to limit the emission of methane and try to diminish the levels of methane by 30%. That makes sense, in fact, because methane is staying 10 years in the atmosphere, whereas if you compare to CO2, it's staying like more than 100 years. So that's like what we call a quick thing. But it will be as complicated as for CO2, so they really need to get organized. So for me, it's not like the COP, it's like a momentum, but the discussion is continuing all the time. And so I think that each country has to find a good way to follow what is decided in this COP. That's the challenge.
At the beginning of my talk, we talked about how well Montreal worked. Take another example, which is the Convention on Biodiversity. Yeah, so lots of promises, we will reverse biodiversity loss, doesn't happen. So the risk for Paris is that the commitments are not met and we don't have a mechanism for transparently viewing every country's emissions. So we need to have those monitoring things in place. Satellites could help here. Yeah, so satellites could give us a big picture, and then perhaps aircraft could give us, a little bit more detail about where emissions are still coming from. But the satellite stuff work for CFCs. We can pin down, sources of CFCs from the satellite data, and that really helped remove some of the historical sources which were allowed under the protocol to continue, but eventually had to be knocked out. So it was great help doing that. And we are in that position with Paris. So, and even if we get all the accords and all the agreements in place, I think the latest first shot at the estimate is that the commitments in Glasgow will bring us to a world which is 1.8 degrees on average above the baseline. That's still not good enough, as Obama said at COP. We've made a lot of progress, but we've still got a very long way to go. And the bit we've got to go is the hard part. Yeah, it's getting that last bit of agreement that we've got to do. So Glasgow may be a start. It may kick-start again after President Trump's decision to not do so much in that area. So, it's a wait and see, but we haven't got much time here before we have to start geoengineering the planet. And that's really difficult because those technologies don't exist. We need them by 2050 if they had to be used. So there's a hell of a lot riding on this.
Yeah, I don't have too much on the policy side, just as a citizen, I think I have a bit of optimism in the sense that it creates the dialogue and the understanding of the population. I think there's a shifting understanding of climate every time we come to a milestone, which I think is good, but it might be backlash as well. It's at the end of the day, it's a political, the people vote the politicians. And I think it's good for that, hopefully good for that. Hopefully the backlash, the opinion of what is being done. Yeah, right. No more questions.
Thank you. If I may want to take over what just Dan said. Say the result of the top line that we end up with sort of 1.8 increasing temperatures. My question is, on which model this is based, because there are many models. So how we come to the figure of 1.8? When you look at what was anticipated at the end of this 21st century, in previous stops, there are all kinds of models predicting variation of temperature, some very high, some much lower. When you take those models today and you look at what they were predicting in the early 2000s, it doesn't match at all for many of the models. So as a lay citizen, when I read in the press, temperature will grow by increase by 1.8 degrees. Maybe I can read it with another model is going to increase by 0.8, and another one will tell me it's going by 3 degrees. Is it an average, the 1.8, an average on different models with the same, I would say, ponderation, or there is one very likely and precise model?
I just want to maybe correct you slightly on the prediction we're wrong. I think when you look at the predictions versus standard is an actually very impressive agreement, even from the crude models on average planet temperature. The second thing is that there are three uncertainties. There's model uncertainty, which is how long your model is. There is scenario uncertainty, that's the politics, what you're going to do. And then there's chaos. So you are bound to have uncertainty. So I'm like your physicist when you say 1.8 not an uncertainty, right? Yes. So and I think this is the political message. They simplify it to the maximum here, to one number in order to simplify the data. Maybe you can get it clearer.
I agree with you. In fact, the prediction were quite right. It depends really on the scenario you are.
Yes.
And so it's not the worst scenario that we are currently, because we have tried to limit the emission of carbon gas already. So it's showing the increase of temperature. And when we say, for example, that you know, we have measured an increase of 1.1 degree, it means on average over the whole Earth. That means 2 degrees, for example, over land. That means even more than that when you go towards the pole, for example. So it's one value doesn't mean much because it means it's an average, and you don't care if it's 1 degree over the ocean. What you care is it's more than 2 degrees over the land, and it's even more than that when you go to Siberia, for example.
Yeah, but your point is a very good point, because this is not translated to the public. I mean, the public will read 1.8, but if we be a bit more accurate in saying, okay, on the ocean it's going to be 1, people won't care too much, maybe around, but that's what's happened. But if they're in their region, or in a region close to where they, as what Dan was saying, where it's close to home, is at home, and you learn it's going to be 2.5, then probably the community will react differently than just have an average figure of 1.8. I don't say it should be in the detail, but it should be more, you know, there are in policy and economics of the UN, they have world regions. We could work that on particular regions, and this probably would be more, would have more impact on some measures to be taken than just one figure.
So I think that was one of the things that was done at the launch of the third UK climate change risk assessment. It goes in various stages. This was the evidence report launch. And the chair of the adaptation committee, Baroness Brown, in her presentation at the beginning, she did this very thing. So she took the Met Office's work on what's called UK SIP 18, which is the latest Met Office data underlying the UK impact assessments. And she talked also in terms about what the observations are showing, as well as what the modelling is. So she said, remember last summer we had so many hot days, which were well above the long-term average. So she brought it home, and it was far more than 1.8 or 2 degrees she was talking about. And then she said, the UK, because people in the UK like to go to the Med for their holidays, they kind of know what 40 degrees is. And they know we don't have 40 degrees in the UK, which is why they go to the Med. Yeah, so 40 degrees is a good example for a UK audience. So she said, in a couple of decades' time, we will have 40 degrees in the UK, and the current high temperature is 38.7, something like that. And it's those kinds of almost headline figures that start to get the British public thinking we best adapt, or we best cut our emissions, or we best buy some electric vehicles. Yeah? So it's those, and that's been quite successful. So to have more discussions with people after that launch than before.
And I think IPCC also took that into account, because in the last reports, you can have a look, there are regional atlases. And so you can zoom on every point of the Earth, and you can have a look on what's going on to happen before temperature increase, water vapor levels increase, and so on for every part of the globe. It's available online.
Yeah, I can understand that, but I'm not convinced that the average citizen is going to visit the IPCC website. I don't think so. So it's a question of communication. I got your point. It's a question of communication. If I may, I have another question. It's about sea level rise. You show pictures, Michelle, graphs, I'm sorry, which now is about 2 millimeters per year. In the early time, people thought it was a linear increase with the time. Now apparently it's more like a square of the time, which is even worse. Is there a model who can predict with a particular scenario what's going to be the rise in 10, 20, 30 years? A reliable model.
I mean, you must then realize that the models are doing all of the systems. They're designed to capture all aspects of our climate, and the oceans are already modeled. So when we talk about projections, the ocean sea level is already in there. Now there are parts of the models that are incomplete potential, and that's the non-unknown or a non-unknown. So for example, the capping between ice shelves and ocean is in some models sometimes a bit too crude. So there are still parts of the model that are risky. I think scientists are often conservative, I would say, because they will say, you know, that's the scenarios we understand. But sometimes there is outliers. There might be a model that doesn't really represent well the ice shelf, the calving events. So there are aspects that could be worse than this. So the models are trying to do the best that we can right now. But, you know, we're always working to improve the models as well. But so these projections are quite well aligned as far as we know for now with what has actually happened. Anything more to say?
Maybe Kathy, you want to
and the simulation of price that helps improve the model. So this is the whole point. We have 20 years of data now, and we can actually do kind of data, what in weather is data simulation. So we can actually see if our model world, our digital twin, our model world is like real, and improve the model representation at home. But there will always be challenges. We might miss something. Our scientific mind must be open to that.
The models are quite powerful though, because they mix different features, like ocean is coupled to atmosphere, and atmosphere is coupled to vegetation and to ice and so on. So they're quite powerful though. I think in the atmosphere, what's difficult to model, it's like the clouds. It's still difficult to model them correctly, but in general, that's most of the uncertainty is coming from the fact that it's difficult to model clouds. But that's important now, because the computing capability has increased a lot, and so when you compare to observations, working really well.
Quickly, that's something, yeah, that's, I agree, that's something we want to communicate also. This is not like the stock market, even if the stock market has a lot of smart mathematicians. This is actually laws of physics. The models are solving laws of physics. It's like Newton, gravity. We're not doing statistical forecasts or mathematical. They are actually following laws of physics. And so when you put your suit on the pan, we know it's going to get warmer. We know by how much. That's what we do. So,
I'm totally convinced.
no, just because some people they hear so much about the stock market that they think everybody does mathematical, statistical knowledge. They don't. The physics is also physical.
Is there another question? Questions? Because I think it's about 8:15 minutes. No, it's not 8:15, it's only been time. One or two other questions?
On the back.
In the back, yes, please go ahead.
I was wondering to what extent satellite data is being currently monetized by companies. For example, to buy and sell land. You said before that, for example, some land might turn out to be useless in a few years' time. So I was wondering if you're aware of any companies that use that data to profit.
As scientists, we have access to satellite data that are provided by agency like ESA or UNISA. But there are other satellite data available by industrial, for example, methane. There are satellites that measure methane and source of methane, but I don't comment too much on that because they are not available to us. In fact, they are satellite data.
I mean, knowledge is power, right? So this is knowledge we talk about. We review every meter square of our planet for the last several years, possibly 40 years. People are waking up to this, and there's big business around that. The comparative program is designed to be freely accessible to everyone for business as well. And that's a huge resource, open access. But yeah, you're right. There are companies that monetize that, and there are also ethical challenges. We are observing everyone from space. We don't talk about much about this, but it's a kind of big world as well. So there's a lot of, as every technology has a lot of positives, also things to consider on the negative side.
I think one of the interesting things in this area is the big five auditors in the City of London. We've all got teams now who are looking at things like climate change. Colleagues down at LSE have did something for the city, the Lloyd's Register. They had an annual prize on risk, and they did some economic estimates that really said that if we didn't adapt successfully, then the insurance risk that was out there was somewhere between 10 and $50 trillion. That makes people sit up. I nearly compiled some data with a talk on this kind of topic, and you can easily find companies now trumpeting in press releases that they've just won, $50 million contracts to help manage American coasts, marshlands, Great Lake areas even. And so it gives you an idea of the big business that's involved. So, I mean, I think this is good because it means there are ways in which investors can now make best decisions about what investments to make in the future. And that will change the game. If an investor says they won't invest because the company is not transparent about its climate, its greenhouse gas emissions, or about other aspects of the sustainable development goals it's trying to achieve, that really will change commercial behaviour. And that inevitably will feed down to the consumer because it will change consumer choices. So I think that whole process is really quite interesting.
I was going to ask you if you think that this is the way to go about it, and you already answered it, because if you see space exploration, for example, you see companies like SpaceX that accelerated the rate of innovation in that regard. And if you wait for governments to take that lead, I think that they will. And so I think you already answered that. Incentivizing companies to go into satellite technology will be a good thing for those sectors.
So we have time for one last question. Jenny. Okay, so I think we're going to bring this conference debate to a close. Thank you again very much, all the speakers. You might want to say closing words.
Well, I would like to thank the speakers for the amazing data that they have presented. It's not my field of expertise, but I really understood very well. Thank you for the clarity of your presentation. And I was amazed by the resolution of your data and how precise you can get. And I think that this is very important for the larger public to also understand what's possible today with the tools that you have. And it's a really challenging topic. And thank you, Serge, for organizing this meeting. Thank you, UCL. And thank you also our colleague from France who took the time to come with us and to join. Thank you very much.
Thank you again.
Thank you.
Thank you. The organizer also herself. Thank you. It doesn't help us so much.
Yes, I should also thank the people who are behind the scene and